pleasure to be here virtually with all of you, being at home or at work or wherever you are. So this is me, just super brief. I'm an electrical engineer by heart, I should say, but I joined product management. So I am currently working for HBK as product manager on our Genesis portfolio. And why this is a very good choice about the application, you will learn later. There's some context if you want to catch me up later on and discuss more, please feel free to do so. So it is exciting times that we're living in because there are a lot of new propulsion technology introduced and they introduce new problems. And new problems are awesome because we as engineers, we can solve them. We can solve them in any way we like, which should just be a very good idea. And one thing is for sure, anybody working on electric aircraft must be a little bit crazy. I'm pretty sure of it because if you just take a look, there's so many. Let me like this one here, for example. This has been bought recently by Air Canada. So they made a purchase of these electric aircraft, and it has 4 motors, 4 electric motors, and it has to have all the batteries. Okay, this is fine that we have 4. Now, if you take what Volkswagen presented here, is an eVTOL with 10 motors. So we have many motors already, and these motors want to be operated as a high voltage, and they're inverter driven. So we have also high frequency in the electrical signals. We have higher phase count and complexity because you want to get every single energy out of the battery that is used. And with all of this comes complications. So we have lightweight motors, and the lightweight motors have a low inductance, and this will introduce problems. Yeah, so we will see current ripple, torque ripple, and a lot of vibrations. And these ripples and these vibrations is nothing that you want to have in your aircraft, especially as it should be in service for a very long time, and it needs to be 100% reliable. If a car breaks down, well, that's fine, right? You just stop at the side of the road. But if your aircraft falls from the sky, this is not an aircraft you want to be seated in. So if you just take a very simplified look on the measurements chain, we at the very front, number 1 is our power source, which is normally a battery. Then we have a frequency inverter that we need, which needs to be top-notch and connected to the electrical engine. And automotive normally stops here at the transmission, and then you're all set. You get an additional complication or different level in aircraft because you also need to worry about the propeller, which is itself not too easy to handle. So in this talk, first, I want to concentrate about this combined approach of frequency inverter and electric machine and which problems we have here. Second one, let's take a look at the whole chain, frequency inverter transmission to the propeller. And then, as we saw earlier, as aircraft engineers they like complex stuff. Then we take a look at, okay, what do we need to consider and how can we test in the best way complex systems? So what system can we use for it? And what we offer as HBK is our eDrive system. And with this system, you have a data acquisition control that can measure at every single point, every single signal that is required. So at the very beginning, we need the power from the power source, so voltage and current testing here. This is also what we definitely need at the frequency inverter output to the electrical machine. But this is only the electrical side. We need to combine the electrical side with the mechanical side. So this is why we need the best torque transducer at the rotating shaft to measure the true mechanical torque that we can get. This is already a plethora of signals, but what you definitely want to add in an aircraft are temperatures. And as we said, NVH becomes more and more important as well, is we also want to have the accelerations in there. All these signals with more signals, there can be various other signals you can see on the left. They are recorded in real time and as raw data. And you can see in real time all the measurements in our perception software. So if I'm talking about perception, this is the software that we have. What is more important for a lot of our customers is that they have their automation system. And this automation system requires data in real time. And therefore, we introduce, or we have here the field bus possibilities like EtherCAT or CAN-FD or via API, where you can access the results in real time with and thus with extremely low frequency latency. So first, let's take a look at motor and inverter and what we need to measure there. So if I have a motor, the motor itself is a source of vibration. This is due to a couple of reasons. So we have the torque, and the torque follows the envelope of the AC excitation. So we have here on the very top right, we see a three-phase system, right? So our torque will somehow sit on top of this curve. And only by this we see there must be some kind of ripple in there. This is a function on the electrical frequency and also on the winding distribution. So there are ways also to reduce the torque ripple in this regards, but there are no measures to completely kill it off. And then in addition, if we have, just for instance, a permanent magnet machine that you see here, we have interactions with a slot teeth. Because magnets really want to stick to each other, right? And once they stick, let's say they are stuck to this teeth, and I want to turn it more, there is a resistance, and it definitely then wants to stick to the next one. And by this is what you also feel when you turn it just manually. You have a ripple of the torque that is a function of the magnet, thus a function of the slots, and adds an additional torque ripple on top. Then we have the inverter. And normally an inverter operation is that we have a PWM modulation. So which means that the AC is created with a pole with modulated voltage that we see here, right? So these the rectangulars we see here on the top, this is a pole width modulation, and by this we get our current. This is what it looks like in theory. In praxis, you can see the measurement that we have below. As we have a PWM voltage, we also have a PWM current. And with this, ultimately, we have also a PWM modulated torque. And this is a source for a lot of noise and vibration at the switching rate of the inverter. So again, here, first we have motor problems. Now we're adding inverter problems. And then we come also to the torque thing. If you take a look here, what you see here is we want to measure the true output of our machine. So we would love to have the torque as precisely measured as possible. But on the other hand, we want the torque also as responsive as possible. Because if you take a look here, we see a ramp up of our measurement signal, and with the ramp up, also the torque follows, right? And depending on the filtering that we have, so what you see here, we have full bandwidth torque, filter torque, and a 10 Hz filter torque. You get different signals. So the full bandwidth torque you see here, it ramps up instantly and follows this slope, while the 10 Hz filter torque is far more stable, but also not as responsive. This is what we meant by this phase delay. So this also needs to be taken into consideration. Now, what happens if we have an inverter and want to get torque? In this example, there is a motor which first was excited via PWM modulation at the first section here, and then we have a switch to a 6-step modulation, which we see in the ladder of this measurement. And we see clearly that there are huge effects due to this. So at the beginning, we see here the torque in pink to the very bottom, and we see this ripple, right? There is a ripple. And as soon as we switch to the 6-step modulation, there is a huge increase in torque ripple. And thus, you need a very dynamic torque signal as well to do these kinds of analysis. Now we have the same measurement. You can see it on the top right. And we look at the frequency domain, because this frequency domain also holds a lot of valuable information. So if we take a look at this measurements right now, first, what you need to show is we had, for this measurement in particular, the bandwidth of the torque was just 1 kilohertz. So this is why here, yeah, these don't add up. Please take it into consideration. And at first, we have the PWM modulation, which is shown in blue, which is basically lower if you cannot see it at home. And after the switch to the 6-step frequency, to the 6-step modulation, you see the same measurement and the implications of it. So let's just pick one here, because there is. So here we have, if we take a look at the mechanical side, at 200 hertz, we see there is a resonance, or we see a spike. Why do we have 200 hertz? The rotational frequency was 50 hertz, and we have a 4-pole machine. So 4 times 50, this is why we end up with a 200 hertz. And with the 6-step modulation, it definitely steps up. We also see the implications of the 6-step modulation here at the very top at the 600 hertz frequency range. This is due to we have 6 switchings in our 6-step at 100 hertz. So this is why we end up at 600 hertz. And these kinds of information are only visible if you have the frequency domain data of all the signals that are of interest for you. And these are just 2 examples, right? There are far more information that you can get by just taking a look at these 2 FFTs. We not only have an input from how we modulate the voltage or the current, but also we have influences by the torque loading on the frequency spectra. So in this measurement, you see another machine. It is a different machine than before, but here there are 3 loads, one at no load at all, one at 30 Newton meters, and one at 26 Newton meters of torque. And then we can see that the inverter signature shows a strong torque dependency, but not only torque, right? And we can also see that switching is always there, but has stronger presence with loading. And we can take a look on why there are the switching frequencies. So there's a strong peak here around 10 kilohertz. And this is why, because the inverter was switching at 10 kilohertz. So we see this influence here. The spikes we see here at 20 kilohertz are due to this machine, which has an inner winding. And there the 20 kilohertz switching frequency is used. So this is what we see here. Okay, so why do we want to measure all the signals, by both the signals? And there are huge benefits of this combined testing. So one is, of course, reduction of costs. This is what everybody wants, right? We just need a single test and not a lot of them. So with a single test, you can already do a lot that normally needed to be done sequentially. So there is a reduction of costs and time. And it is easier with this to do the communication between the groups. So also you get faster development. And you can use it for different applications as well, like sound design and fatigue characterization are normally quite independent, but you can do it with a single measurement, right? Also failure testing, resonance testing, end-of-line characteristics, and so on. So what we see here in this graph, we have the voltage and current on the top. We have the load cell thrust as a second, which I will come to you in some slides. And we also have vibration. Yeah, because as seen before, you should definitely add also possibilities to record your vibrations that you see during the test. So power. So far, we just spoke about voltage and current. But voltage times current gives us a couple of powers. And this is extremely important because normally you would just have the true power output. And we want to have it dynamic because electric motors can be quite dynamic, especially if you start, stop, or change a state. Yeah, there are losses associated with the state change. So what you see here in this measurement is a power. And what we have here, we can calculate the power on what we call half cycle. You see here, let's try to grab one here, the square, whoops, the square one is our half cycle detection. Yeah, so we definitely see here, these are the half cycles that we do our power calculation based on. And this is very, very dynamic. And with this, we can see that at the beginning there, we have a large reactive power during the transient, resulting in inefficiencies, because nobody wants reactive power, right? So where does the reactive power comes? It becomes heat. Yeah, so dynamic power measurements need to be there to understand the actual efficiency during the use of the machine. Okay, so now we know why we should measure the accelerations, voltage, current, power. We understood how the frequency inverter has its thing to torque ripple, while the electrical machine itself has a component to torque ripple and also to vibrations. Now we want to take a look, okay, if we want to do a thrust stand measurement, what do we need to take into consideration? So this is an example of a thrust stand where we have standard electric powertrain measurements. But here, also the propeller efficiency now needs to be included. So we need to have thrust in addition and airspeed in addition. Also, we want to know the resonant vibrations, right? And everything is done at a high fundamental frequency. So the test stand is here. You can see in the very back, there is a load cell. And here is the AC motor. Yeah, there is a torque sensor integrated here to get the mechanical power. And at the top, there was a replaceable mount, maybe to check for different propeller configurations. So we know how the propeller efficiency is calculated, which is fine, but we want to have it in real time to get the insights as early as possible in our test. So what we can do is we can calculate complex values in real time based on the half cycles of the power. So as we know the measured thrust via the load cell, and we have a measured airflow and measured torque, speed, and all the electrical signals, we can now calculate powers and efficiencies in real time in the data acquisition system itself. So these real-time values can be fed back to the automation system. Or let's say, for control, for instance, or if you want to go into the realm of hill testing. So these information are there at any test engineer, whoever needs them. What you see here to the right is what we call our real-time formula database. And there you can define literally any formula that you need, that you want to measure in real time or that you want to get calculated in real time. This is done on the board's DSP, so as early in the process as possible. And with this, we see a picture of the test stand that I just spoke about in the top right. And there are, this is an example of a 3-phase propeller on load during a startup. So what we have here is also a measurement of this motor. So we have a startup. We see, so we have the startup here. We see the steady state here. And then somewhere here in the back, something went wrong at this test. So all 3 phase voltage and current are measured. And we can see here we have the power, the reactive power and apparent power in parallel at all time. And these values can be calculated. We can see them during the test, and they can, of course, be stored in real time at the full sampling frequency. So there's only one measurement system for diverse set of tests, right? Because now what we add here is what we said before. So we have the thrust and the airflow and at the top here, which are measured. Yeah, one is with a load cell. The airflow is measured with a sensor. Then we have the voltage and current, which were measured directly or with a current transducer that you need. And thus you can calculate the power and efficiencies in real time of the propeller power and propeller efficiency, the inverter power and inverter efficiency, and the battery power. And as you see here, all these plots are plotted as scope trays. And already during testing, if there is an event you want to, you cannot wait to analyze further, you can do what is called review while recording. So you leave your recording going, and you can review and zoom in the data that is already recorded and stored. So there is no time to miss, right? If there's something interesting, just jump right on it. Okay, so now we go to the next level. Currently, what we had so far is just one stream. But as we saw before, like electrical aircrafts or eVTOLs, they have multiple of these trains. So we need multiple of our problems. And this is what you see here. We have multiple motor and we see a possible test setup. So a quadcopter performance evaluation. Okay, we want to do inverter efficiency testing and also a system control test. So what we have here is, we call it eDrive configurator with a setup screen. So we have a single battery here. Yeah, here's a battery. And we have here in the second row, let's the inverters, and here we have the motors. What we can do is to calculate any efficiency for any individual strain or from any individual point that we are interested in. So we can calculate the efficiency, let's say, from the battery. If you're just interested in, let's say, this motor 2 to the end of the motor 2. So what is from what we get from the battery to the actual torque output at our second motor. And this is extremely flexible. So this is not predefined. You can define it as you wish. So maybe you have a second battery here, right? So you don't have battery like here, but you have a second battery for motor 3 and 4. This can be set up as individually as your test is. And with this, it is quite easy to handle large channel counts, right? And we have the possibility to minimize the post-processing time with all the real-time calculations. So this is what it could look like. We have high channel counts for voltage and current, and we incorporate these data with the mechanical signals. On the very top here, you see the measurement for the voltage and the current at the battery. While here, there are 3 measurements for 3 motors where we have the individual currents and voltages of the motors. And on the right-hand side, you see here the power that is drawn from the battery or the power that is drawn from the individual motors. Everything at one glance. So here we have a total recording of 30 seconds of flight with all channels, recording at 2 megasamples per second, which is for how long the hard disk has place. You can record at this data rate. And it is, an easy tool to visualize all these things. So for instance, you can see here that motor 1 is very constant, right? And has here also very, very constant power output, Whereas motor 2, some here, is a lot more really not as straightforward as motor 1. So some control is going there already. And the motor 3 already has a different, also has a different kind of power output. And with all these tools simultaneously having the data, you can start ditching into the reasons. Maybe you wanted to have it like this because you had some kind of control algorithm and maybe it was unexpected. Okay, so we not only have the real-time calculated thrust, the measured power, the measured voltage and current, but also way more signals here. So as you see here is all the signals that we are interested in got integrated into a single data acquisition system. So the electric power, the load cells, the accelerations, the temperatures, and also the displacements were all captured within a single device. With this, we could reduce the instrumentation complexity. You don't need to worry about different data acquisition systems that you also need to sync and cannot see the whole picture in real time. Yeah, it does significantly reduce the instrumentation costs, and it enhances the measurement efficiency in operational conditions. And it is quite flexible, right? So no matter which system you're looking at, you have a system which can handle like any amount of data. Okay, half an hour in. I won't grab you for a whole hour. So at first, to sum up, what we have here or what we show is if you want to do testing for electromechanical systems, it is good to have a system that already suits all needs. So we have time-aligned data that allows system-level analysis, not only in the time domain, as we saw here, but also in the frequency domain, right? Because this is where a lot of interesting insights are. You want to have both, not exclusively one or the other, because you want to have both to understand the true effect in your aircraft or in your eVTOL. And with one system, who can does it all, you have the possibility to streamline the validations with just a single test. So you can already look at the efficiencies of all your motor, and still in parallel, you can already look at sound and vibration and control and calibration within a single goal. So different working groups could use the same set of data and do their magic on it. And you can feed, or for sure, feedback these data to the simulation guys or to the structure guys. They have all the same set of raw data, and they can be sure that all the required data are in there. So what value do we provide to the customer? As said, we have a simple data collection of all electromechanical signals. They're fast and accurate in efficiency measurement, and they're quite future-proof. So if you say, okay, I need more data to be added, more accelerometers, you can extend our system. If you say, I have way more data, so let's say I just had 4 motors for now, and now I need to add 6 motors or 7 motors, which I need to analyze. Then you can sync different mainframes via optical Ethernet, and it will run just as one system, although it almost doubled in channel count. We have auditable testing. So as you could see, once we store all data as raw data, nothing is changed in there, and all the equations that you use are public, right? So all the equations that you introduce, for instance, for thrust measurement or for whatever reasons, they are public. You can review and see them. You can also review and see all the equations that we do for the power calculations. So everything is there, everything is open and can be controlled. And we provide real-time feedback to the control system to let it do its work via field bus. So we have from the sensors to the software to later on to the automation system, all in a single package. And I think with this, I'm done so far. Thank you very much.